Okay, so this will be solving RLC circuits. Some people were having some issues between discerning whether they needed to find initial conditions or solve an RLC circuit. The purpose here is to solve the circuit for IL of t. We're trying to find an expression that depends on time for the current going through the inductor. We're not finding initial conditions here. We're already given these two that we have to work with to find the solution for this problem. So this is solving RLC circuits. The first thing that you should do is try to simplify the circuit so that way you have either a simple, clean parallel RLC or a series RLC. For this example, we're almost there. Of course, we have a voltage supply, time-dependent current supply, and a resistor here. But through some transformations, we'll get this down to a simple parallel RLC circuit that we can then apply the rules to that we learned in class. So now you can see I have a circuit where all of the elements are in parallel. So the voltage across here and across here, across here for VC and VL and VR is all the same. So everything is in parallel now. So based on that, we can combine these two resistors by using the equivalent resistance for parallel resistors. So this will be 40 times 10 over 50, which is 400 over 50, which equals 8. So our equivalent is 8 ohms. And with this, we are focusing on positive T. So this time dependent current supply will just become 6 amps. Because for positive T, the step function is 1. So for all positive T, this will be 6 amps. So now we have 2 current supplies that we can combine to get one 9 amp current supply. Okay, so now we have an incredibly simplified circuit. This is what we want. We have our R, our resistor, is equal to 8 ohms. Our L, 4 Henry inductor, and our C, which is a 10 millifarad capacitor, or RLC circuit. It's in parallel, so we need to remember the equations for our S1, S2, alpha, and omega naught. Okay, so we have our 2 characteristics here. This is our resonant frequency, and the alpha, which will tell us the dampening characteristics of this circuit. For alpha greater than the resonant frequency, it'll be overdamped. If they are equal, they'll be critically damped. And if alpha is less than omega naught, then it will be underdamped. Okay, so I went ahead and calculated our resonant frequency and the alpha, and we found that alpha is larger than W naught, than omega naught rather. So this would entail that our circuit is overdamped. Now, pay attention that when you're making these calculations, the difference between millifarad and microfarad. Millifarad, which is what we're dealing with here, is it corresponds to 10 to the negative 3 farads. So you'll see that 10 millifarad came out to be 0.01. So convert all your units to their bases. So now we can pull out the equation for the natural V of t or I of t for an overdamped circuit, and also the equation for our S1 and S2, which will be the coefficients in the natural equation in the exponent over the E. Okay, so now we found that the circuit is overdamped, so we're going to move on to finding the natural response of the circuit, Vn of t, and also the forced response, Vf of t. Vf of t is relatively easy in this case. For a very long time after this circuit is activated, or however you want to say it, L will become a short. So that means that the voltage between this node and this node will be 0. So we can just write that V forced of T equals 0 volts. Let's calculate our natural response. So we need to find S1 and 2. We can use this equation here. In this case, that S1 is equal to minus 2.5 and S2 is equal to minus 10. And it doesn't matter which one you label as S1 and S2. So now to solve for K1 and K2, the coefficients in front of the E's, we will use one of our initial conditions. So we know that for Vc of 0, V is minus 20. So at t equal to 0, the E's will go away because the exponent will be equal to 0. E to the 1 is 0. And we will have that minus 20 is equal to K1 plus K2. And we can say that K1 is equal to minus 20 minus K2. So we have one equation with two unknowns. We need one more equation to solve for K1 and K2. We can use our second initial condition that was given, the dVc dt at 0, to get our second equation. So I'll do that now. So now, between these two equations, we can solve for K1 and K2 using either linear algebra, matrix techniques, or just using simple algebraic techniques. And you'll find that K1, in this case, is equal to 13.33, roughly. That's negative 13.33, excuse me. And K2 is equal to minus 6.67. We have our S1 and S2 and our K1 and K2. We can substitute that back in here, find the natural response, add the forced response, which is just 0. So we will find our final solution for Vc of t. So here is our solution for V of c of t. But you'll remember the problem is asking for IL of t. Now there are two ways to make this relation. Either you can use KCL on the circuit to find the relation between the voltage between the two nodes and the current going through the inductor. And the equation for that would be IC of t is equal to C dV dt. And remember that dV, that V, L, and VC are the same because we're in a parallel circuit. Or you can also use the relationship that VL equals L times DIL dt. Okay, so we come to our last step here. In this case, I would say that integration is easier, but it's probably better that we understand the relationships between the currents and the voltages, and also how to use KCL in this case. So starting with KCL, we have on this top node 9 amps going in and IC going in, because in the problem it said that our capacitor orientation was with the negative side up, so current through the capacitor will be going this way. Current for the resistor and the inductor going down, so that leaves us with this KCL here, 9 amps plus the current going through the capacitor equals the current going through the inductor plus the current of the resistor. So we rearrange that, we find that 9 plus C dV dt, this is IC, plus VC of t over R, this is the current going through the resistor, is V over R, equals IL of t. That's what we're trying to solve for. So now we know all these values here. We know V of t, so we just take the derivative of that to find dV dt. We know C, and we have an expression for VC of t, that was the original VC of t here, and we know R. So we just plug that in, and we get this ugly looking thing here, but you'll see we have the 10 millifarad capacitor times, this is dV dt plus VC of t, or just V of t, over R, plus the 9 amps from the